Hi there. Welcome back to Talking Tech. We're still at virtually CES 2022, and we're having a special episode as a crossover with Intel Chip Chat. That's our podcast. I have special guests today, two of the designers behind Alder Lake. That's a code name for 12th Gen Intel Core. It's a great conversation. Let's get right to it. All right, Tomer and Arik, thank you so much for joining me. I know the original plans had us all together in Las Vegas, but of course, plans change, but I'm so glad that we're able to talk virtually here. So thanks so much for joining me from Israel.
Thanks for having us.
Thank you for having us.
Yes, of course. And first of all, can you start off with your name, your title, and what you do? Why don't you start, Tomer?
Sure. So Tomer Sasson, I'm the Alder Lake platform program manager in the client computing group for Intel. Been with Intel for 25 years, managed interesting projects in the past like Sandy Bridge and Ultrabooks reference designs, but Alder Lake is probably the best and most interesting one I've ever done.
Hi, I'm Arik Gihon. I'm the SoC architecture lead for the Alder Lake project. I'm like 18 years at Intel, have previous experience in architecture and main expertise in power management, but also different other areas.
Wonderful. Well, you're both great contributors to Alder Lake, and I'll say I'm a big fan. It's one of the most exciting CPUs that I've seen in a long time. I'm a big fan. I think that the die here from the Core i9 desktop S is a thing of beauty. In fact, I kind of like it so much. I had a custom hoodie made. So this is something that I had to have done because I'm a big fan. You got the P cores, you got the E cores. So I'm just gonna wear this today. I think it's great.
Wow.
Okay. But yeah, let's get started. So I first want to ask you, this Alder Lake family at CES, we revealed the entire family, right? Going from 9 watts from the ultra portable all the way to the 125 watts full K SKUs on desktop. How did you create a design that supported such a scalable a range of processor needs?
I think that the beauty of the Alder Lake program is that it was designed up front as a family of products. From the design phase throughout the validation, the manufacturing, the platform aspects of it, all the way through the last moment before launch. It was designed that way such that we can really, for the first time, bring 4 different products to the market in such a short period. And we have a few more to come. So we're absolutely not done with Alder Lake yet.
Is there anything for you to add to that, Arik?
Yeah, I totally agree. We started, by thinking on one SKU, but we knew that we have to support with one architecture actually the entire portfolio of the client segments. And this was a pretty big challenge because you need to satisfy all vectors all together while one segment doesn't need everything. So this made us think quite a lot on architecture, what features we need to add and what things we need to do in order to cope with the entire challenge of supplying the entire family with one scalable architecture. So this was a big challenge.
All right. So you just said challenge. What was the most difficult or the most challenging thing that you had to overcome during development of Alder Lake?
Yeah, so first is understanding what we actually need to do and what to optimize and which solution we need to have in order to indeed give a solution that can scale from a couple of milliwatts on the mobile segments to a couple of hundreds of watts in the desktop segment and bring the best performance we can bring into the table. And actually, one of the things that we explored and understood is that you cannot, with a single type of architecture and a single type of general purpose computing, actually satisfy everything. And therefore, we had to come with some hybrid architecture and COP solutions that will meet more than what we just do typically.
From my perspective, from the execution point of view, of course, it was the pandemic, right, that hit us just at the beginning of the post-silicon execution. And we really had, to scramble and figure out solutions such that the project can continue. It started off when we actually split up the lab, the validation lab in Israel. We actually used multiple of conference rooms and training rooms that were empty in the building and transferred them to B Labs space such that we can, create few capsules and, minimize the physical interaction and get the project going. And, as we approach the critical milestones, the end of the project from, at least on the desktop side, we got hit on the Bangalore side. India went from, okay, let's wait till 5 p.m., then no work on weekend, and then no work at all for a couple of weeks. And that was, the most critical phase of the project. And, I'm glad to say that the teams in Israel, Bangalore, and all over the world really stood up to this challenge. And it practically didn't slow us down by a day.
And I know that, processor design, like such as Alder Lake, these things take years, right? This is years in the making. I know people expect a new processor every year, but this stuff is years in the planning. How far were you into the development of Alder Lake when the pandemic flared up and affected, your workflow?
Yeah, we already had the silicon in-house. So we already started testing and validating the silicon pretty much. So it got us in the preparation for, the most critical phase of the program, which is the post-silicon execution. Were
there any learnings from developing a processor during pandemic times that will influence the way that you approach things in the future?
I think, we learned that we can do such complex project without so many travels. When we started the project, I promised the team in Bangalore that I will pay them a visit, and that never happened. So I still owe them one. I really don't know when that's going to happen. Hopefully soon, really hopefully soon. But that's part of it. We used to do big face-to-faces, bring people from all over the world. Let's take Power as an example, right? When you first get the first silicon, we used to bring experts from all over the world in the different domains to bring up the silicon. This time we did it virtually. And you know what? We found out that it's possible. Now, is it a good thing? Probably. Is it the right thing to do forever? Hopefully not.
Yeah, I get, when dealing with these billions of transistors, I suppose all the thousands of people have to get together and really celebrate these really major milestones.
Yeah, I still hope we'll get to celebrate this properly. We enjoy the CES, we enjoy watching the events, but it's not the same thing. So I really hope to be able to celebrate with the entire team properly.
So another question, just go back to some of the challenges. I asked in the beginning about the scalable design, but I want to hear more about the pros and cons of having to develop an architecture that has to support everything from high-end desktop all the way to ultra mobile. Can you give me some of the quick pros and cons of things that you have to consider?
Yeah, definitely. So, when you're developing something that is general purpose and has to fit to many type of use cases and big power envelopes, a wide range of power envelopes, you obviously cannot optimize for everything. So everything that you want to optimize, if you want to optimize something, you need to do something that is specific and has a special purpose inside. So you will be able to give the best that you can do for this segment. So obviously we have done a couple of compromises, but we are very satisfied with the result, meaning that we had to develop things that will be general purpose, but also behave in a heterogeneous way so they can satisfy many different vectors. So, and this is, as I said also previously, hybrid and heterogeneity is one of the things that you actually need if you want to satisfy different vectors in one architecture, as well as scaling your architecture to be able to work with different type of sizes, different number of cores, different number of ports, and so on. So this requirement, or actually this was a decision we made, which led to quite a lot of decision later on the way we want to architect things. And eventually it paid off because it is rather optimized to the segments, and yet we were able to supply with one architecture the different segments, and there is a lot of upside also for doing this, because eventually when you look on the client, everything is PC, and the PC has to behave in a similar way. When you optimize one thing, you probably optimize it for multiple segments. When you implement something, it applies to many other segments as well, so you earn from that. You don't need to validate everything altogether. So we indeed gained quite a lot, and this also enabled us to give quite a lot of PRQs in such a small time frame. Obviously, you need to do here and there some optimization per segment, per type of die, and so on. But this was the right trade-off eventually.
And you mentioned optimization. So given that that Alder Lake has so many different configurations across desktop, mobile. In fact, right now I'm wearing the 12900K, so I have 8 P cores and 8 E cores. Can you tell me, how did you determine the optimal mix of different core types?
First, I must say that optimal is a problematic word because it's never optimal, and you can always do some nitpicking and look for a more optimal configuration. And in addition, when you want to optimize a configuration, you really need to look on the use case, on the scenario, on the power envelope. Each of them has a different optimization point. So you need to look in a broad type of scenarios. You need to understand for each segment what the user actually wants, and then select the one that fits it the most. And I believe that since the architecture was scalable, we were rather able to actually find a good enough topology to satisfy what we want. And when we choose it, we just went on with that, and later on added a couple of additional tweaks to the architecture in order to optimize within this configuration that we have selected already.
I think the important thing here, to complement what Arik just said, is that this is a foundational change, right? We are laying the ground for the decade to come in terms of the architecture and the product mix that we're going to be offering. And the mix of P cores and E cores, like Arik said, it's a point solution, and it may change in the future. If you talk to us again, in CS23, we may have other products and other configurations and other optimization points coming out.
Tell me more about the collaboration between the P core and E core teams.
I would say that just by having to plug those two different cores into a one SoC, we mandated cooperation between the teams. Because you need to cooperate in terms of instruction set, you need to cooperate in terms of set of features, coherency, same interfaces and protocol, power management, power delivery. The two teams had to work together and by SoC directing the type of features and requirements, and eventually bring one solution that will fit one SoC. And of course, the SoC had to do different type of adjustment since eventually those are two different architecture with different characteristics, and you need to satisfy both. So I would say there was quite good cooperation between the teams. They learned each other, optimized for whatever we have requested, and eventually you see the results. Both cores are working under a single cache with a single power management entity, sharing multiple resources. So obviously the cooperation succeeded.
From my perspective, again, the collaboration across those two teams was tremendous. And it started with a pretty long kind of a negotiation phase, right? Deprecating features, adding features on the other side to get to a similar ISA such that eventually we can manage this machine. I think it was a pretty complex project and a pretty complex definition phase, at the beginning of the project, which eventually yielded a pretty good product.
The two microarchitectures behind P core and E core for Alder Lake, that's Golden Cove on the P cores, and that's Gracemont for the E cores, and of course that comes from a long line of coves and monts. Would it be accurate to say that these microarchitectures were originally designed separately, but of course they have to come together? And if so, does the performance hybrid for the future influence how the next generation microarchitectures will be developed?
Well, I would say that, those are two x86 cores. During the development of Mont, obviously the teams are aware of what the COVs are doing, and there is sharing and learnings, but eventually if you put the teams together and make them develop the cores completely in alignment, then you get eventually the same core. But this must not happen if you want to support something that is hybrid, something that goes into and solve two different problems. And therefore, the two had different targets. They had different targets. They eventually ended up with different characteristics, and they solved two different problems. And I would say that they supplement each other. So yes, each of them had to look on the other side and see what's going on and whether they optimize the same thing. But eventually you need to satisfy a certain requirement, and therefore you end up with the different animal, I would say. Both are very powerful cores. Both are supporting the same ISA. Teams and methodologies that we develop are similar, but you take the design and tweak it to fit the envelope that you want, and you get the hybrid solution by that.
So you mentioned two teams. Do you think that there's any spirit of competition between the two of them?
Yeah, I would say, there's always competition, but the teams are grown enough to know what's their role and what they need to optimize. And I think in that aspect, and you can see, just by looking at the sizes of the cores, they are different. They are different in the size, they are different in the structure, they are different in what they give eventually. Both of them are very ambitious teams and wants to be the best, but the best in what the SoC eventually requires.
I think the two of them coming together, right, is eventually what makes Alder Lake so unique, right? And the different implementations, as Arik described them, are actually bringing the value to the product. So each of those core teams is, running on its own and developing the best they need to develop and meeting their KPIs. But eventually stitching them together and bringing the solution to the market is where the magic happens.
And I think one thing is, instead of just highlighting, and we've been talking a lot about the coming together, the marriage of the P cores and E cores, but even the gen on gen leap in performance is quite remarkable. So I wanted to ask about the P cores. What are some of the biggest contributing factors to that really big gen-on-gen increase in IPC for P core?
Yeah, I think I wouldn't say there is the biggest or several big features that gave everything. I would say that it's across the board of optimization. I think every pipe stage was optimized from the front end to the through the execution and to the memory. There's smartness that was added into the different structures, as well as increasing the structure in order to supply more performance. A lot of smartness was added to the front end, better prefetching, a better prediction of branch prediction, bigger UOP cache, bigger UOP queues, out of order, which is wider and stronger, more execution ports, smarter and faster floating, adder, another load port, and so on. So I would say that it was across the board, and there's no one bottleneck that needs to be solved in order to get more IPC out of the cores. It's a mature course. You need to solve multiple bottlenecks and that get this big IPC improvement. And all of that with also making sure the power is not going up too much. So I would say they did a great job going over the entire microarchitecture and optimizing things, and you see the results. It's pretty good.
Yeah, I would add two more items in terms of the SoC to platform collaboration. First of all, of course, is the memory technology, right? Going up towards DDR5 on the desktop side and LPDDR5 on the mobile side. And specifically on desktop, dedicated effort and a lot of focus on overclocking. Adding specific features, adding new capabilities, and addressing specific overclocking headroom. And you see that in terms of the number of world records that were broken shortly after the desktop launch, and global first place, even with the i9, i7, i5 configurations, which emphasizes the overclocking headroom we have in the product.
Oh, of course. I was talking to Dan Ragland here in Oregon, and he had a lot of great things to say about how fun those E-cores are to overclock. So let's move on to E-cores. Besides their space efficiency, and I've seen that a cluster of 4 E-cores fits into about one of the one real estate of the P-cores, which is certainly impressive. What other aspects of E-cores or E-core contributes most to its really surprisingly strong performance.
Yeah, I would say there are two additional kind of high-level, I would say, benefits that comes with the E-cores. One is the ability to utilize bandwidth, cache bandwidth and memory bandwidth by clustering the 4 E-cores and having a big L2 serving them. The bandwidth utilization on the last level cache and the memory is better, and therefore you can utilize the resource better and consume less power, which eventually yields more performance and more efficiency. And the second, it's not more for performance, but basically it gives us the ability to go into lower envelopes because the core is smaller, and then if you want to consume less power regardless of energy and so on, then you can go and draw much less power. So I would say those are the two. In addition to the area density, which is a big factor.
Yeah, and there are probably two firsts, with this E-core family, right? First of all is first time we implement those on the Intel 7 process, right? And second is first time we really bring E-cores to the masses in terms of a high volume product that spans, over the entire, client ecosystem, with millions and millions of units. So that's where we really, see E-core, shining for the first time in volume that they've never seen before.
I want to ask a question about the platform, and that's about, you mentioned DDR5 earlier, but we also have another leading support for PCIe Gen 5.0, and there was a demo that we just released just a few days ago. Can you tell me a little bit more about that PCIe storage demo, in fact?
Sure. So let me tell you a short story about this demo. When along the process of developing Alder Lake, we were ahead of the ecosystem because, you cannot obtain today discrete graphics or an SSD, which is PCIe 5 based. So, we had voices saying, okay, guys, you're driving something that you cannot even test, you cannot even validate. How can you say that you support PCIe 5 when the ecosystem is not there? And, we drove the team crazy. We told them, hey, we're going to do this. I don't care where the ecosystem is. I'm going to be ahead of the ecosystem. We are going to be ahead of the ecosystem and let them chase us once and for all. Okay? And the team developed internal testing and validation capabilities and developed the exact steps they need to take in order to ensure that we really meet the PCIe 5 spec, including the available certification, and show us that, they are entitled to the title PCIe 5 ready. Okay, and it wasn't trivial. I think, we got it done pretty much at the last minute before releasing the product. And I'm happy that, the team stood up to this challenge. Otherwise, you wouldn't see that demo. Okay, you've just seen a couple of days ago. And the ecosystem is still not there, by the way, right? SSDs are probably a year out, and discrete graphics probably give or take the same, right? We don't really know when those are going to show up. But desktop has a strong aftermarket, volume, and we believe eventually you and users like you will be able to upgrade an Alder Lake system to PCIe 5 based discrete graphics or SSDs.
So along those same lines, with Gen 5 SSDs set to arrive before Gen 5 GPUs, and hopefully supply will be much greater then, why don't we support natively segmenting the CPU lanes into X8, X4, and X4?
Yeah, I think we just assume that Gen 4 bandwidth will satisfy storage, at least for Alder Lake timeframe, and we aimed Gen 5 to satisfy discrete graphics. I think this is the main reason.
And bleeding edge, of course, is DDR5. Same story. Finding this cutting edge technology can be a challenge. But one of the great things is that Alder Lake also supports DDR4. So I imagine that this must present some design complexities. So what were the challenges of supporting 4 memory types through a single PHY?
Wow, it's I would say it's a big complexity because you cannot optimize everything, and you need to have the different type of training, different type of handling inside the memory controllers. The protocols are different. The handling of each type of the DDRs, both in terms of the amount of different speeds that they are supporting. as well as validating each of the topologies. We are supporting memory frequency changes and different speeds, and therefore we had to select for each of the technology what will be the optimized points that will go with each of the technologies. Another aspect was the combo PHY, obviously. Combo PHY is a big thing. No one does it. And actually, Intel invested quite a lot, and it works. And this was, I would say, a big achievement to the PHY team. They are very proud of giving the combo PHY, and it works with the two technologies.
Yeah, from the platform side, again, working on 4 different memory technologies in parallel is unprecedented. And specifically, DDR5 and LP5 were developed, hand in hand with Alder Lake. So, when we had the early silicon, they had the early silicon. And when you run into problems, guess, who is to blame and how do you fix the problem? And then you need to wait for them to spin off their silicon and we need to spin our silicon. So it was, it was an ongoing process that eventually, took time to converge across both the DDR5 and the LP5 domains. It was part of the, most fascinating stuff that we've done on Alder Lake is really, to be first to enable those technologies in the ecosystem and being able to support all 4 different technologies at the same time.
And not only supporting new technologies, but also the performance hybrid architecture. You're integrating 2 different microarchitectures in a single SoC. Is it incrementally 1.5 times more difficult, or is it twice as difficult to support 2 compared to just doing a single homogeneous design?
Oh, well, how to quantify it like that, but it's significantly, it's significantly complex comparing to a single microarchitecture. Both because of the interactions, you need to interact with 2 teams, you need to have some compromise, and you need to eventually design it to actually work with those 2 architectures, which are different in their characteristics. I can give you a couple of examples. If you want to put them under a single cache with a single power delivery, then what do? It's not only power budgeting, it's resource budgeting. How would you set the frequency? How would you set the voltage? How would you optimize the operation? Sometimes they work together, sometimes they work separately. They do share the cache as a resource. How do you divide the resource between the small core and the big core in order to optimize performance? You also have priorities on different usages, which are different. Take into account, you have more than just one module of E-cluster. How would you schedule it? Would you do first the B cores and then the E cores? Would you do one on the E core and then one on the other module of the E core? Would you first fill E cores together and then switch among them? So I would say just by going into hybrid architecture and just by having those in front of us opened a huge range of things we need to think of when we optimize. And I think we did a huge mileage in optimizing things. And the good things for us, at least, that we think that we still have a lot to do and still have a lot to optimize. So you still have margin to optimize and get more from this architecture. If you look on the platform level, software level, and the OS, this yet opens another challenge to face with, which yet being added to the complexity, because it's not just that you develop your CPU and then you hand it over and it works exactly as you wanted with every software or every OS. Software needs to be optimized when it's running on the CPU. And one of the things that we have thought was that, the way we work, we supply CPU to every box in the world, has to work with every OS, every software with a lot of legacy. We need to keep it as much as transparent from the application. And this is why we have selected a solution together with Microsoft and cooperated together with them on bringing a solution that is mostly transparent to the application, involves the OS on scheduling, involves the hardware, tries to do things decoupled between the 2. And eventually, I think it ended up just fine.
I've obviously I've noticed we've talked about how flexible the Alder Lake design is, but with the announcement of the whole full family, there are variants that have just six performance cores only or 4 performance cores only. Are these completely different designs, or are they do they share a lot of commonality with the ones with P cores and E cores?
No, there is a lot of commonality. Of course, this was done to provide a price performance optimized segment of the market, mainly on the desktop side. The SoC design itself was developed up front to accommodate this option. So it's not something that you do after the fact, right? It was designed that way up front. And eventually, it was a rather simple project to do as long as the definition was done right.
I should have asked this immediately following up from what Arik said about software, but I want to revisit how much of the Alder Lake design hinged on the way software would operate with the processor.
Yeah, I wouldn't say we relied only on software and software optimization. I think we did quite a lot, and the majority of I would say the essence of the technology also comes from the CPU. We invested quite a lot, in the cores and in the SoC to be able to understand what is actually running on the CPU. It's something that we never did in the past. We had quite a lot of telemetry that we have inside the core, pretty good and well-established architecture to be able to understand what is actually running in terms of characterize the nature of what is actually running. So when you look on instructions that are running and the behavior of the core, you are able to actually understand what the application is doing. Together with that, we advertising that into the SoC level and then advertising it to the OS through the memory, and in addition to the type of application, looking at the scenario that we are running, whether it's lightly threaded or fully utilizing all the threads, whether you have IOs utilized, and so on. Together with all of that and the power envelope, we were able to actually put some guidelines, some hints to the OS saying you need to do this and that. And I would say, it's relying on the SoC, on the software, but it's easy to shift between different type of OSs. So I would say the majority of the support is in the CPU already.
In having the OS scheduler work with 12th gen, we've developed technology called the Intel Thread Director, which helps to put the right thread on the right core at the right time, especially with Windows 11. Of course, it's coming to other OSs too, like Linux in time. But in relative terms of challenges, how difficult was it to implement and develop something like Thread Director?
It was difficult. It involved quite a lot of teams around the globe. It's not only the SoC team in Israel. It's platform teams in the US. It's software persons. It's a meeting with Microsoft that did terrific work on that. So it involved a lot of parties. You need to enable the ecosystem for this feature to work. So you need to understand in software, you need to understand what platform is doing, you need to understand the CPU. Obviously not one person, not one team that can do that. And therefore, every feature that is actually an integrative of multiple teams that comes from the different areas of expertise is always difficult. You need to understand the different languages to eventually get the best results. So I would say it's a complex one, but I think as you can see, it is working, and it is working directly while we have shipped the parts. So it ended up very good.
And I would add that this is all done in parallel to Microsoft developing Windows 11, which is probably one of the biggest jumps on their side right in the last few years. And they have their own constraints and their own schedule and their own problems that they need to resolve and bring the product to market. And I must say that the collaboration between Intel and Microsoft to get this solution on time to Windows 11 to meet the constraints of both projects, right? Both the Alder Lake project and the Windows 11 projects was a tremendous collaboration, and I think both companies should be proud of the end result.
I think based on everything you're telling me, I think that the level of complexity in developing both hardware and software together cannot be understated. How do the power management challenges compare for the P&E cores that we've been talking about versus the other elements of the system, like the SoC, the memory controller, PCIe, and internal fabrics?
First, everything that you develop for the first time is more complex. So every technology that you deal with for the first time is more complex than incremental changes that you have on other parties that you are already familiar with. When you look on the memory subsystem, PCIe, the set of features is actually different than the set of features that you have for the cores. You mostly update idle power on PCIe. You have a very defined states. Memory subsystem is the destination of the compute, and it's handled almost the same incrementally on different generations. So I would say it's much bigger than just PCIe and memory subsystem. And from power management perspective, the first thing you need to do is making sure that those different cores, while they are different microarchitecture, they work seamlessly together. Both needs to work and work under similar power budget, thermal budget. They are sharing currents from the voltage regulators on the platform, same battery, they are competing resources. You need to make sure both are supporting all the set of features, and the need to actually calculate things per different type of cores is a very complex thing. And therefore, one of the things that we went with is to make sure that we treat those cores evenly in terms of power management, until the point that you need to select which best for performance or for power in terms of optimization. So functionally, they support the full set of features. By the way, just didn't mention, but eCore is supporting the entire set of feature. The core is supporting 4 generations. So it did also this leap, joining the core in all the different type of power management tweaks and tricks that we did in the previous generation, turbo, budgeting, software interfaces, and so on. So we brought them into the same stage. So it took time, and it's much more complex than memory subsystem and PC.
I asked before about collaboration between the teams that work on the SoC, but can you also tell me about the collaboration between the team that designs the SoC and, of course, the overall platform down to the chipset and across both desktop and mobile? What are the collaborations between everything to bring one big platform together?
Yeah, sure. I'll take this one. I think that, Alder Lake was a great example of, cross teams and cross geos collaboration. We practically managed the software integration of the platform in a continuous integration mode. We had the kind of a daily stand-up, like a Scrum meeting, pretty much, that, when you bring all the experts to the room and make sure that every bit of the software is being tweaked and changed to support whatever the silicon and the platform needs at that time. And the great collaboration between the SoC team and the platform team enabled us to deliver timely both samples of hardware and software codes to our OEM partners across the globe and across the different projects. And we're running most of them, many of them in parallel, both the desktop and the mobile projects. I would say this collaboration was tremendous, and it's a great opportunity to thank the team on both sides for this collaboration and bringing both the hardware and the software together to the market.
Well, it sounds like there's a lot to be proud of and a lot to celebrate. So I have to ask, Tomer, you're talking about, coming together virtually for Power On, but what did you guys do to celebrate when, Power On, or even the release of Alder Lake? Did you do anything special to celebrate, either by yourself or with your teams?
No, at least in Israel, we tried. We had an internal webcast. We communicated to the employees, at least, trying to share the excitement. We provided specific, a newsletter to the employees with the highlights of the launch event and the press coverage that went along with it. And we're probably going to do something similar next week, following up the CES excitement. Beyond that, waiting for COVID to calm down, and hopefully we can celebrate, bigger, just like we like and just like we did on prior projects.
What about you, Arik? And the only reason I'm asking is, here in America, people, have the joke of when something, they hit a great milestone, they say, "I'm going to Disneyland," or something like that. Are you gonna take a vacation? Are you gonna buy yourself a new car or something like that? How do you
no, I think the satisfaction and I think it's enough. I think the phone calls we had between the teams saying, it actually works after so many things you do in one project. It's actually amazing that it works, and the boot was so fast this time. We were amazed, and I remember not only the boot, I remember the really short time after boot, looking at all the packet C-state actually working functionally, and say, wow, how come it actually works out of the box and so on. We knew we have a long way to actually optimize things, and until silicon is mature to be PRQ'd, but I think this was the satisfaction when you do such a big thing and eventually it end up working, and you identify problem, but you do see a very good signs. I think this was satisfying enough, and the team really felt good about it, and a lot of motivations to the next project and the next challenges. I think that it also opened our minds to do more, think big, take risk, and I'm hoping at least in architecture this is the spirit that we need to take.
And of course, in the world of engineering and design at Intel, you guys never sit still. So what's next for you guys and your teams?
So I'm working on the next gen beyond Alder Lake already. GB disclosed it in few words at CES. He called the project codename Raptor Lake. And he said that, we already have silicon booting in the lab, so I can say what GB said. And, we're busy with that, and that will keep us busy in the next year for sure.
Yeah, in my end, Raptor Lake as well, but we are also looking at the next generation. After that, cannot tell you too much details, but it is exciting, and I think the market has what to look for. We are trying to be aggressive.
So no vacation here.
Well, after COVID, I think we all deserve a long getaway to someplace tropical and nice. Well, I'm a big fan of Alder Lake, big fan of your work. I have even a deeper appreciation for all the work that goes behind a design of this, and all the teams that have to come together, both in person and virtually. So I look forward to Raptor Lake and everything else beyond. So Arik, Tomer, thank you so much for taking the time to join me virtually. It was really enlightening, and I really can't wait to follow up with you guys once we have the next one that we can talk about.
Thank you.
Yeah, hopefully next CES we do this face to face.
We'll do this all over again with the new processor. Thank you so much, guys.
Thank you.
Thank you, too.
All right.
That was Arik and Tomer joining me virtually from Israel. They're a couple of the designers behind Alder Lake, that's 12th gen Intel Core processors, and what a treat it was to learn about the intricacies and the making of Alder Lake. This was a special episode of Intel Chip Chat, kind of presented to you from the desk of Intel Talking Tech. It was a real pleasure to have that conversation. I'm so glad I can share it with you here. Of course, there's plenty more on the Intel Technology channel, and of course on wherever you get your podcasts for Intel Chip Chat. Thanks so much for joining me, and I look forward to the next one. See you soon.